Hey, good day, guys. Welcome again to my channel. This is Joshua, the designer. It's been a while on this channel. All right, it's good to be back together with you. And may I say Happy New Year? All right, so I'll be taking you through series of design sessions. All right, and I'll be taking you today bolt connection. In this video, you'll be learning how to design a simple bolt connection. All right. Okay, so when we talk about the bolt connection, there are basically two things that characterizes the strength of any bolt connection. All right. So the design strength of any bolt connection, all right, the design strength of any bolt connection is either in the shear capacity or the bearing capacity. All right. So if I would break this down further, all right, so we might say that the possible failure modes, all right, so there are possible failure modes when we talk about bolt connection. All right, so these are the possible failure modes. We have the shear failure of bolts. So we all to know all this. We have the block shear failure. All right, we have the bearing failure of bolts. We also have the bearing failure of the connected parts. All right, so you would see that we're having the shear failure as I've explained in the first part, and we also have the bearing failure. All right, bearing failure modes. Now the design of both connections are simple, all right, but we need to follow the recommended procedure following our BS code, all right, BS 5950. All right, so every recommendations as touching both connections are registered in the BS code, and we have to pay attention as we go along our designs. All right, so I'd like to take us through certain recommendations even as we proceed in the design of this particular um, problem. All right, in this particular problem, we'll be taking through our BS code and we'll check through recommendations as we proceed. Now, let's check this question. It says a lap joint between plate 65 mm by 8 mm is shown below. All right, so we have the plate shown below. All right, and the lap joint. This is a lap joint. We also have the butt joint. All right. Okay, so it transmits a factored load of 45 kilonewton using black bolts. Now, black bolts are also called the non-preloaded bolts. All right, and we also have the preloaded bolts. The those are different from the non-preloaded bolts. All right, so of 16 mm diameter and grade 4.6, the plates are made of steel of grade S275. Check the shear capacity. Now we have what we are to look out for: the shear capacity, all right, and the bearing capacity. All right, and these are the two things we are looking out for, and the bearing capacity. And also we are looking for the number of bolts. Calculate the number of bolts. Calculate the number of bolts required to make the connection. All right, also find the pitch and edge distance. That pitch there is another way to say that is the distance between each bolt. All right, the distance between bolts. That's another way of saying that. We call that also the bolt spacing. All right, so let's just go ahead and begin from somewhere. Now, I said there are recommendations starting from the clearance of your holes. There are recommendations, so I'll take us through the BS 5950 so that we can start from somewhere. Now, there is a table in the BS code, BS 5950 table 33. Let's just look for that table. I mean to show us something from there. Table 33. Table 33 says standard dimensions of holes for non-preloaded bolts. I mentioned the fact that that kind of bolt you're having there is a non-preloaded bolt. I mentioned that. All right, so the nominal diameter of bolts on the first column. All right, then we have the standard clearance hole. So if you mean to use 12 diameter bolt, for example, in your connection, it means that the standard clearance hole that will be provided when you are preparing your plate for the connection, all right, would carry a standard clearance hole of 13 millimeter in diameter. Considering 16 also, it will carry a standard clearance hole of 18 So if we simplify this to as a formula, all right, we would say that for every bolt less than 16 for every bolt diameter less than 16 you have the diameter plus 1 to have your standard clearance hole. All right, for 16 for bolts between 16 and 24 you have the diameter plus 2 to have your standard clearance hole. And that's exactly what we see here in the BS code. You see down from 16 to 24, it's just adding 2 to your bolt diameter that you have the standard clearance hole. All right, so down to 24 you have that. But when your diameter is greater than 27, when diameter is greater than 27 it changes to 3 So your standard clearance hole will be achieved, will be calculated with this. So you may stay with this formula or you stay with your table, who would give you the same value. All right, so if we are going to start with that which you have already declared already, we are going to say that for the bolt diameter given here, black bolt of 16 diameter, the standard clearance hole, which we could denote as capital D, all right, would be small d plus 2 based on what we saw right in the code. So these are first consideration from what we have in the question, plus 2. So we have 18 standard clearance hole. All right, okay, I believe that's very clear enough. Now from the question, we know D is 16 so we have no trouble on that. Now another thing that we would want to look to is the pitch and edge distance. From our question, you discover that was clearly stated that we should look for the pitch and edge distance. All right, and I said that the pitch is also the bolt spacing. All right, and the edge distance can also be called the end distance. So they might interplay those words, pitch as the bolt spacing, while we use the edge as the end distance. All right, okay, so for the second one I would like to show you is that of the pitch and edge distance. So in the code of practice BS 5950, you will find bolt spacing. I'll show that to you. Bolt spacing, and that's under clause 6.2.1 of our code. So let's get to the code and see what it says. 6.2.1. So we have edge and end distances. All right, edge and end distances. So we have for standard clearance hole and for holes for fitted bolts, the edge distance should be taken as the distance from the center of the hole to the adjacent edge, all right, measured perpendicular to the direction of stress. The end distance should be taken as distance from the center of the hole to the adjacent edge, measured in the direction in which the bolt bears, all right. The end distance should be sufficient to provide adequate bearing capacity. So we are checking clause 6.3.3.3 and 6.4.4 so that we can see what to use. Now the minimum edge or end distance which was required of us, which is required of us rather, the distance from the center of the bolt to the edge or end of any part should be not less than the value given in table 29. So whatever end distance you've been given should not be less than the value we are going to see right now from table 29. Okay, so let's set table 29. So for a rolled, that is machine flame cut, sun, or planed edge or end, we are supposed to stay with 1.25 D. For a shed or hand flame cut edge or end, we are going to stay with 1.4 D. But in this question, we are working with a rolled, a manufactured element. All right, so we are staying with 1.25 D as recommended by the code. So the value should not, as said here, should not be less than 1.25 of the standard clearance hole. All right, so let's get back to our calculation. So for our minimum spacing, and remember that this minimum spacing is talking about that for bolts, which is the pitch or the bolt distances. Now what we have in the question here is 50. As you can see, that what we have in the question is 50. So we are going to check if this 50 is sufficient or not. Using 1.25 of the capital D, all right, we have 1.25 in brackets 18, which we have already determined earlier, and that would give us 22.5 mm. All right, so going back here, minimum edge or end distance. Okay, so the end distance that we have here, says we should not exceed 22, should not be less than, should be greater than or equals to 22.5 mm for the end distance. All right, so let's work with that approach. This is the end distance. All right, end distance, end or edge distance. All right, but what we have here is 35, all right, which is less than 35, which means it's okay. All right, so what we have there is quite okay to proceed with, seeing that as the code recommends that any value that we have here should be less, should not be less than 1.25 diameter, all right? And what we have here is 35, which is quite greater than 1.25 of the diameter. So we are good. So this is the minimum. Now let's check the maximum. There's also the maximum. This is the minimum. Then we have the maximum edge distance. That is the value with which the provided one we have in this question should not exceed. All right. And if we go back to the code, we'll find that also everything is captured in the code. Maximum edge or end distance says where parts are connected by bolts, the distance from an unstiffened edge to the nearest line of bolts should not exceed 11 T epsilon. All right, 11 T epsilon. So we have 11 T epsilon. The T is the thickness of the connected part, that's of the plate. Then we have the epsilon. We can obtain the value for epsilon can be obtained using this simple relation. All right, epsilon can be gotten with this relation over py raised power 0.5. all right. So to get this done, we need to know this py. Let's see if we have that from our question. All right. So we have the plates are made of steel grade of grade S275. Of course, in S275 we have several strengths of steels there. All right. So we need to be sure of which to work with. So you can't just pick 275 because they said grade S275. If you do that, you might not be so accurate, especially you might not be so lucky, especially if your thickness of your plates do not fall in the category where 275 would make you that lucky. All right. So because it's not a guesswork, and that's why we have the code of practice to work with always. So I'll take you to where you can quietly confirm everything you're working with so that you'll be a little more accurate. All right. So if you check what we have here, we have 8 mm thickness. That's the thickness of your plate, 8 mm thickness. And I'll show you how that this is important in determining the strength you're supposed to work with. All right. Okay, good. Now let's get back to our code and we'll look for table. Let's get down there. All right, everything you would need is right here in your code. All right, so I'll show it to you. We are going down to table now, table 9. All right, so table 9 speaks of design strength, py, and that's exactly what we're looking for. The steel grade that was given to us is S275. all right, but you see that under S275 you have these different design strength. We have 275 down to 225. So for you to know which of the design strength you're supposed to work with, it is determined it is a determinant of this thickness is a determinant of which of them you're going to go with. All right, so we are working with a thickness of 8 mm, which is quite less than 16 mm. all right, so it means that you are staying within this range, 275. all right, you are working with 275. Peradventure you have a thickness greater than 16 mm but not up to 40 mm, not greater than 40 mm, greater than 16 mm but not greater than 40 mm. We can say like greater than 16 mm, less than 40 mm. all right, you are going to stay with 265. Also, if you have a thickness greater than 40 mm but less than 63 mm, you are going to stay with 255. all right, so but for this we are going to stay with our 275. So we are not working with a guess, we are working with the code. All right, so this py here is going to be 275, meaning that our epsilon is going to give us 1. Now the thickness is 8 mm like we said. We have 11 multiplied by 8, then multiplied by the epsilon. So there we have the value of 88. All right. Okay. 88 mm. So we see that what we have as the spacing, the end distance 35 mm, is less than 88, which is the maximum edge distance. So we are good to go. That's fine. All right, so to move on, we have the pitch. Now we have done, we are quite good with the end distance. All right, so the pitch, let's check for the pitch now. So which I also said you may call the bolt spacing. Bolt spacing itself. All right, the bolt itself. All right, this is the heading of the clause. All right, so let's stay with that. Now for the bolt spacing, now we have the minimum bolt spacing or minimum spacing. Now our code have recommendation for this. So let's check quickly. We'll go back to our clause 6.3.3. All right, so those should be with you handy so that you know where to go when you need them. All right, 6.3. 6.3, a little more. All right, or 6.2 rather. 6.2 was what we found the, yes. So we have the edge or end distance. We are done with that. All right, so let's check for the bolt spacing itself. 6.2. Yes, minimum spacing. The code says for standard clearance holes or holes for fitted bolts, the spacing between center of bolts should not be less than 2.5 D. You see that? Should not be less than that for bolts. So we have the minimum now. What we have should not be less than 2.5 D. And what do we have? Checking from the question now, you discover that what we have is 50. So it means that 50 should not be less than our result here. And what's going to be our result? 2.5 in the bracket, 18. So we're going to have 40. So definitely 50 is not less than 40. We are good. So this is good. For the maximum spacing, all right, the code also has recommendation. It says that where a plate is not stiffened by web or outstand, the spacing between centers of adjacent bolts in a line lying in the direction of stress should not exceed 14 T. All right, so it means our 50 should not exceed 14 T. All right, so we have this to be 14 in the bracket. The thickness is 8, and that's going to be 15 multiplied by 14 multiplied by 8 will be 112, which is quite all right. Okay, so with this we've been able to sort out the pitch and the end distance. All right, which I believe by now it should be clear enough for you to grasp. Now, to go ahead, we're just going to check the shear capacity of the bolt. You know, I said earlier that one of the possible failure modes of bolts is the shear failure of the bolt itself. All right, so let's check that quickly as we proceed. The shear failure. All right. Shear capacity. Now the idea is this. the basic principle is this: your factor design strength should be greater than your factored load. That is the load that the tension or the compression or the load that produces moment actions around your connection should not exceed the capacity of your bolts in shear. That's the principle. All right. So once you calculate your bolts capacity in shear and it exceeds the tensile force or the compressive force, all right, usually tensile force, all right, you're good, you're good. But if not, you need to try a higher bolt, a higher diameter of bolt for now, for the benefit of the shear effect. All right, so we have for the shear capacity now. I'm going to take you also to the clause, to the BS code. All right, we have provisions for this or also in clause 3.6.3.2.1. all right, so in doing this, let's check what the code says on shear capacity. All right, so for shear capacity for non-preloaded bolts, all right, we have PS, which is the shear capacity we were talking about, is equals to small ps, which is the shear strength, multiplied by the shear area. And there is something in particular. It says AS is the shear area, or AT, and that AT is supposed to be the tensile area. But there is a provision as to that, as defined in 6.3.1. If you want to get that clear, let's just check it. It says where it can be shown that threads do not occur in the shear plane, all right, AS may be taken as the shank area. All right, shank area is the area that the end that which is not threaded. All right, so we have why the tensile area is the threaded area. Okay, so we have the shank area A. In the calculation of thread length, allowance should be made for tolerance and the thread runoff. So where it is clearly shown that shear doesn't occur in the shear plane, all right, you may take your AS as the shear area. Okay, let's go above. There's something I need to show you. The shear area AS of a bolt should normally be taken as the tensile shear area AT. Did you see that? The shear area should normally be taken as AT. That's the tensile area, all right, as specified in the appropriate bolt standard. For bolts without a defined tensile stress area AT, did you see that? If you don't have a tensile stress area defined, all right, so your AS should be taken, your AT should be taken as the bottom of the threads, which will be equal to your shank area. If your tensile stress area is not defined, your AT can be taken as AS, all right, which is the shank area. So let's proceed and see how this affects our own enterprise. All right, so with this, for the shear capacity, we have PS is equals to PS AS as defined by the code. Now the PS here, the small PS that I call this small PS can be obtained from the code of practice, is the shear strength, all right, from table 30, as you can see here. So let's check table 30. And of course, we have been given grade 4.6 in our question. It has an equivalent shear strength of 160 Newton per millimeter square. All right, so that's what our PS represents here, 160 Newton per millimeter square. Now our AS, for this, according to what the code says here, it says if for both without a defined tensile stress area AT, we can take the value of AT as the shank area AS. All right, so but there are values for, you can check out values for the tensile area. All right, for every bolt there are tensile stress area for every bolt. We are using a 16 bolt. It has a tensile area of 157 millimeter square. All right. So please work with that. Please work with that, because the tensile stress area can be obtained and you know it. So that's 157 millimeter square. There is actually a table for counter grade if for different grades. All right, we have grade 4 point we have grade 10.9. all right, we also have grade 8.8. we also have grade 4.6. all right, so as it affects your application, so please do stay with it. All right, so you can check your BS 5950, BS 4190, BS 4933 for this table for tensile area. Okay, so for this we are good. Now you can apply this to obtain your value. So we have 160 multiplied by 157, and this should give you 25.12 kilonewton. All right, so this is the shear capacity of a bolt per bolt of one of 116 diameter bolt. All right, now to check the bearing capacity of that bolt, I told you the failure mode of a bolt could be in shear, and also could be in bearing. So, and that's why I'm doing this. So to have that, there is a formula also in the code. So everything you need basically is just your code. So we have your bearing capacity. So let's go ahead and check. So you find the bearing capacity of bolts, clause 6.3.3.1.2 rather. So you have the formula here. D is the nominal diameter of your bolt. T is the thickness of your connected part, while your PBB is the bearing strength of your bolt. So let's apply that and move on. All right, so we have PBB is equals to DTPPBB. All right, so the diameter, remember that this is a small d. All right, so that's going to be 16. Don't make that mistake. Thickness of your plate is 8, and PBB can be obtained from your code, which is the strength, bearing strength of your bolt. All right, so for 4.6 grade, we have 460 as the bearing strength. So we have 460, and that will give us 58.9 kilonewton per bolt. Do not forget. All right, so we're done with that. Let's get to see which of the questions we are yet to answer. All right, so we've done the shear capacity, we've done the bearing capacity, we've done the pitch and edge distances. All right, so we are left with the number of bolts. How do we then obtain the number of bolts? It's quite simple. All right, this what you see right in the question doesn't mean it's going to be 2 bolts necessarily. This is just figurative. It's just for you to see that bolts are being used in the connection, and hence you have to do your calculation and be sure that whatever bolt you're using is adequate for that connection. So how do we get the number of bolts? Number of bolts. All right, so let's just be imaginative. You have a force to resist. You have a force to resist, and the question says we have 45 kilonewton force. In case you did not see that, let's get back to the question. In case you did not see that, we have it transmits a factored load of 45 kilonewton. Did you see that now? All right, so it transmits a factored load of 45 kilonewton. So let's see how we can deal with that. Now let's be imaginative. Like I said, we have a 45 kilonewton force to withstand or to resist. All right, so it means that the bolts we are to provide should have a shear capacity greater than this. It should have a shear capacity above this. And for our calculation, we observe that the shear capacity of a bolt is 25.12, meaning is less than this force we are supposed to resist. So how do you get that? Now, the number of bolts now, just by the normal mathematics, all right, would be the total force to be resisted divided by the shear capacity of one bolt, and see how many bolts would then need for this connection. So we have 45 kilonewton divided by 25.12 that we have gotten earlier. This will give us 1.79. Of course, we know that there is nothing like 0.79 volts. All right, so we'll round this up to mean two numbers of volts. All right, and checking it just for check purposes. All right, just for check purposes, we have 2 multiplied by the capacity of 1 volt. You see that it's quite greater than is greater than 45 kilonewton. We are above 50 kilonewton. You see that? So it means that 2 number of volts is sufficient for that connection. All right, there are other things we could check at this stage, but for this question we want to stop here. All right, since we have checked for the shear capacity and the bearing capacity of the bolts, we have calculated the number of bolts and we've done the edge and the pitch distances. All right, so in the next tutorial I'll be showing to you how to calculate the bearing capacity of connected parts and the tension capacity of connected parts. In case you want to go further for a full calculation of this setup, then you will be good. If you have any questions as touching this particular tutorial, you may use the comment section, as I'll be there to answer all of your questions, your comments, your queries, your suggestions. Thank you very much. If you haven't subscribed to my channel, you can do that now. You should do that now. All right, so till we meet in the next tutorial, I am Joshua the designer. Bye.